Microsoft might be good at AI research, but they are great at PR. They coined the term one-bit LLMs, which sounds punchy, but really it's more of a metaphor. The giveaway is in the title of their BitNet paper. They're not really one-bit LLMs, but actually 1.58-bit, which begs the question, what the heck is a fractional bit, and how do you store it in real hardware? Okay, so that was my Eastern European voice, which is casually telling you that there's no Santa. But I also have an adopted American voice, which is a lot more optimistic and is actually quite excited about a future where we run LLMs locally on consumer hardware with full privacy. This video is part of a longer series on quantization, but it's fully self-contained. We'll talk about what LLMs are, how we can run them effectively with the hardware that we have today, how good they are, and what's the chance that they'll become mainstream one day. So let's dive in. Let's start with the inspiration behind one-bit LLMs. On a philosophical level, the first BitNet paper from Microsoft draws a parallel with human biology. It quotes none other than William Henry Gates III.
I'll cheat a little bit.
Right, that Bill Gates. He says, I don't think there's anything unique about human intelligence. All the neurons in the brain that make up perceptions and emotions operate in a binary fashion. A biological neuron is binary in the sense that, given an input, it either fires or it doesn't, so its output is either 0 or 1. In contrast, in one-bit LLMs, the binary weight values are -1 and +1. The reason is -1 is more expressive than 0, allowing us to negate the input features. But sometimes we want to have our cake and eat it too. That's why there's another category of LLMs that use all three values instead. The benefit of including 0 is that we can ignore irrelevant features. Of course, the trade-off with ternary values is that we need more than one bit to store them. More exactly, we need at least log base 2 of 3, which is 1.58 bits. From now on, I'll be using the term one-bit LLM rather loosely to refer to either of these two variants. So why would we go to such extremes? Well, the motivation is straightforward: faster inference with lower memory usage. When you convert model weights from 16-bit or 8-bit floating point down to a single bit, you get a proportional reduction in memory requirements. And because modern accelerators are bottlenecked by memory bandwidth, fewer gigabytes also means faster inference. And not to mention, the checkpoints are smaller and easier to download. So, one-bit LLMs aren't just academic, intellectual candy, they do translate to real-world gains. BitNet runs inference 9 times faster on GPUs and 6 times faster on CPUs compared to full precision models with the same parameter count. BitNet might be the first one-bit LLM, but the idea of binary models has been around for a while. In 2015, when deep learning was focused on image classification, we saw the first convolutional neural networks getting quantized to 1 or 2 bits, including Binary Connect, Binary Net, and XNOR-Net. In 2018, the BERT model was dominating text classification leaderboards. And shortly after, quantized models like Binary BERT, BiBERT, and Ternary BERT came out. And then by 2023, LLMs became really capable, and that's when Microsoft released their first BitNet paper. The original 2023 version of BitNet was truly one bit and had binary weights. But less than a year later, it got upgraded to ternary weights in the now famous paper, The Era of One-Bit LLMs. What's more exciting is that just last month, in April 2025, Microsoft open-sourced a 2 billion parameter version of ternary BitNet, so you can grab it yourself from HuggingFace. Now that's nice, but the paper does mention larger models too, up to 70 billion, and it doesn't look like we're going to get our hands on them anytime soon. And some of us are disappointed about that. What exactly are we supposed to do with the weakest model? But I'll leave the complaints for later. When preparing for this video, I asked you what you found most intriguing or curious about one-bit LLMs. And there were a lot of thoughtful answers, but one of them stood out. At first, I thought the commenter hit return too early, but then I realized, no, that's it. That's exactly the reaction I had the first time I heard about one-bit LLMs. How? How can they possibly work? Let's talk about the bitnet model architecture. At a high level, bitnet looks like any other modern LLM, a stack of transformer blocks. The key innovation is one simple change to the transformer block. In a nutshell, a classic transformer block has two main components: self-attention, followed by a feed-forward network. For the purpose of this video, you don't need an in-depth understanding of them, but if you're curious, check out this video I made a while back at Google explaining the transformer architecture in detail. All you need to know for now is that within these subcomponents, there are multiple linear layers. In PyTorch, these are simple torch and nonlinear objects that multiply an activation x by a weight matrix A and optionally add a weight vector or bias B. In modern LLMs, the bias B is usually omitted, so a linear layer is literally just a single matrix multiplication and float 16 precision. Now, here's how BitNet modifies this standard transformer block. It's really simple. Each linear layer is swapped with a custom bitlinear layer. BitLinear is also a matrix multiplication, but its operands are no longer in full precision. Activations are 8-bit integers and weights are ternary. This might sound very surprising, but other than this bitlinear swap, there's no other change to the model architecture. Everything outside of the bitlinear box works as before in full precision. That includes, for instance, the attention computation and everything else outside of the transformer blocks. For instance, the token embedding matrix that turns tokens into vectors remains in full precision. So the secret behind one-bit LLMs is that they're not really one bit. They're still parts of the network that run in full precision, and even within bitlinear, it's only the weights that are ternary. The activations are stored either in 8 bits or more recently in 4 bits. But that's okay, we don't need to be purists about it. Quantizing even just the linear layer brings huge gains because these layers dominate the computational cost. So the whole magic is neatly packed in this bitlinear layer, and the engineer in me is oddly satisfied by this decoupling. From the point of view of the rest of the network, bitlinear is a black box that takes in full precision activations and outputs some transformed version of them. Then naturally, on entering this box, there needs to be a quantization step converting them to 8-bit integers. And on exiting this box, the reverse needs to happen to dequantize them back into float 16. If you're interested in the exact mechanics of going from floats to integers and vice versa, check out my previous video on quantization fundamentals. Now, the core innovation happens here in the middle, where we multiply 8-bit activations by ternary weight matrices. It turns out we can implement this much more efficiently than general matrix multiplication. When the only multipliers are -1, 0, and 1, computing the elements in the output matrix reduces to additions and subtractions. So there are a lot of interesting optimizations that can be done here, and we'll get into the weeds a little bit later. But there's one extra critical ingredient needed to make bitlinear work in practice, and that's a layer norm inserted before quantizing the activation. This shifts the activation mean to 0 and its variance to 1, which is a crucial property for multiple reasons. First, the symmetry around 0 makes quantization easier to implement, something I covered in my previous video on quantization fundamentals. And second, it makes quantization resilient to outliers. Let me give you a counterexample, a misbehaved activation where the first coordinate is a huge value like 120, while all the others are closer to 0. To preserve this difference in magnitude, quantization would have to squash most of the other coordinates to 0, and thus lose a lot of information. Layer norm prevents this catastrophe by homogenizing the activation. So, BitLinear is straightforward enough that we deduced it from first principles. But if you're familiar with post-training quantization techniques like smooth quant, you'll know that they're more complex and they involve a lot more tricks. So you might be rightfully wondering, is this it? Are one-bit LLMs so simple structurally? Well, the reason why they're so elegant is because of the way we train them. One-bit LLMs wouldn't be possible without a process called Quantization-Aware Training, or QAT for short. As you know, AI models have two life stages: training and inference. Inference consists of a single forward pass through the model. An input X is combined with the model weights to produce an output Y. For a lot of tasks, the exact output value doesn't even matter. For instance, when predicting the next word in a sentence, we don't really care if Matt has probability 0.321 or zero point 0.3, as long as it's somewhere in the top. And because inference can tolerate some loss in precision, we can actually run it with quantized weights. So, a natural point in time to perform quantization is right after training. The strategy is called post-training quantization, or PTQ for short. Basically, we train the model in full precision, business as usual. Then, right before deployment, we quantize the checkpoint, mapping each floating point weight to an integer. This is what happens today with a lot of open source LLMs. Providers like Meta and DeepSeek throw us over the fence full precision models, and then the open source community picks them up and quantizes them. This is a viable solution when quantizing to higher bit widths like int8, but it starts to break down when going as low as 1 or 2 bits. This is where quantization-aware training comes in. Instead of treating quantization as an afterthought, we'll expose the model to low bit weights in its early childhood. It's a little bit like exposure therapy. Here's how it works. During training, we'll preserve a master copy of the weights in full precision. We'll use this during the backwards pass to compute gradients, update optimizer states, and nudge the weights in the right direction. It's critical that these operations remain in full precision because model updates happen millions of times and errors would accumulate beyond repair. But here's where things get interesting. Before the forward pass, when the model makes a prediction on a training instance, we will quantize the master weights on the fly. So the forward pass works with ternary weights, just as it will later on during inference. This is also known as fake or simulated quantization. This is the exposure therapy. And to be clear, these ternary weights are temporary. They're thrown away immediately. On the next training step, they are recomputed from the master weights again. Let's see what this means for BitLinear. So far, we only discussed the forward pass when an activation X gets quantized and multiplied by ternary weights. Well, during training, we'll grab our weight matrix from the master copy and quantize it on the fly. So the only thing we need to do is add this extra quantization node. Well, almost, because at this point, you might be raising an eyebrow and asking, how is this differentiable though? The quantization process, as I explained in my previous video, involves lossy operations like rounding. There's no derivative for the round function, so how are we computing the gradients? The answer is the Straight-Through Estimator, or SDE. This is one of Hinton's many contributions to AI. It's a fancy name for saying we're going to bury our heads in the sand, pretend rounding never happened, and set this derivative to the neutral value of 1. SDE has been extensively studied, and there are some mathematical guarantees, but they only hold for very simple models. Given the complexity of LLMs, we're basically just lucky that, in practice, it's a good enough approximation. Originally, QAT was applied throughout the entire training process. But for LLMs, which are trained in multiple stages, QAT is often just a fine-tuning stage after regular, full precision pre-training. This paper from Meta recommends splitting your training budget into 90% full precision pre-training and 10% QAT. By now, it should be clear that quantization makes inference more efficient, but not necessarily training. If anything, fake quantization adds a little bit of overhead to the training process. So, to the NVIDIA haters online, I'm sorry, but Leather Jacket Man isn't going out of business anytime soon. Speaking of hardware, let's talk about storage. For now, we'll ignore the fractional 1.58 and assume we allocate 2 bits per weight, which is a slightly wasteful but simple starting point. So, how would we store a 2-bit number? Well, most modern hardware doesn't support an int2 data type. We've simply never needed it. So we have to simulate it in software using existing data types. In this example, I'll use an 8-bit unsigned integer. A naive but convenient solution would be to store each 2-bit number in its own unsigned int 8. That leaves 6 unused bits, but allows us to use built-in arithmetic. Addition and multiplication work out of the box. But of course, this defeats the purpose of quantizing below 8 bits. The whole point was to save space. An alternative is bitpacking. We can pack 4 2-bit weights into a single uint8. Now, instead of treating uint8 as a standalone number, we interpret it as a sequence of 4 couples of bits. The trade-off is, now we need to write custom logic to unpack these values before performing operations on them. So far, we've assumed 2 bits per weight. This is the best we can do if we encode values separately, where each of the ternary values gets its own encoding. But in machine learning, we rarely deal with scalar weights. They mostly come in matrices. To encode values more effectively, we could group them and encode each group as a single unit. For instance, let's consider a group of 3 values. There are 3 to the power of 3, or 27 possible combinations. We can assign each combination a unique label, or encoding. And to represent these 27 indices, we'll need 5 bits. The result is, now we're only using 5 bits to store 3 weights, reducing our average storage to 1.67 bits per weight. That's pretty close to the 1.58 theoretical lower bound. This strategy is called element-wise lookup table, or ELUT for short, and is what BitNet adopted. They consider 2 versions of it. The one we just discussed, which uses groups of 3 weights stored in 5 bits, is called TL2. TL stands for table lookup, and 2 is just a badly chosen, confusing version number. The other version uses groups of 2 weights stored in 4 bits and is called TL1. TL1 might seem like a step backwards because we're back to 2 bits per weight, but it might actually be more convenient as a storage format because 4 bits are easier to pack into an int8 than 5 bits are. Let's take a quick look at the checkpoints available on HuggingFace and investigate how weights are stored. So there are 3 checkpoints. We have the original one in bfloat16 precision, which is useful if you want to perform further fine-tuning. Then we have 2 quantized checkpoints. GGUF is a binary format introduced by the authors of llama.cpp, a general inference engine for LLMs. We might discuss it in a future video. And I believe this 3rd checkpoint uses the TL1 format that we just discussed. Here, we're looking at the diff between the tensors in 2 checkpoints. Full precision on the left side and quantized TL1 on the right side. Certain weights, like this down projection matrix over here, get converted from bfloat16 into uint8. And it's interesting to look at the sizes of the tensors as well. This matrix goes from 2560 rows down to 640, which is 4 times less. That's expected because a single uint8 packs 4 weights at a time. We're also seeing certain weights, like the token embeddings, preserving their bfloat16 format even in the quantized checkpoint. And finally, we're seeing these new scale weights, which help with the dequantization process, the one that converts integers back into floats. So now we know how to store ternary weights, but what about computation? How does BitLinear perform matrix multiplication efficiently? Imagine a ternary weight matrix W in which the pattern +1 + 1 -1 appears multiple times. When multiplying W by an activation vector X, this duplication pattern translates to repetition in the output matrix. For instance, we computed x1 plus x2 minus x3 three times. This waste adds up in a world where matrices have thousands of rows. We can address this inefficiency by pre-computing lookup tables before performing the matrix multiplication. When grouping three activations together, we'll have 27 cached values for each group. Then, when performing the matrix multiplication, we can simply accumulate these partial results from the table. Caching is just one of the many tricks that can be applied. Actually, earlier this April, Microsoft released bitnet.cpp, a lightweight C++ runtime for efficiently running ternary LLMs. It was intended for CPUs, but they also added GPU kernels recently. If you want to learn more optimization tricks, check out their GitHub repo or the official paper. Okay, so the technology is cool and all, but the real question is, are one-bit LLMs competitive, or are they just a thought experiment? There's an official bitnet demo with the small 2 billion weights model if you want to vibe test it. There's an option to run it on a CPU or an A100 GPU just to get a sense of its latency. I tried my go-to difficult question about PPO, a reinforcement learning algorithm, and the response was borderline incoherent. Granted, it's a high bar because none of the non-reasoning models get it right, including GPT-4o. Then I softballed it with a more basic question: what is PPO? The answer wasn't exactly wrong, but kind of lazy and repetitive, reminded me of a fourth grader. And finally, I tried a gotcha question from simplebetch.com, which contains a lot of distractors. This one in particular asks how many ice cubes are left 3 minutes after placing them on a hot frying pan. And it fails. But maybe vibe checks are not fair because, as users, we're calibrated to huge proprietary models, like the ones behind ChatGPT. Though this does make me resonate with this comment on Reddit. A more fair comparison is against other open weights models with 1 to 2 billion parameters. This table compares full precision models like Llama 3.2 and Gemma 3 against BitNet, and we're seeing BitNet falling right behind the leader, which is Qwen 2.5. Not too bad given that BitNet takes up 6 times less memory. We know there's also a 70 billion version of BitNet that hasn't been released, and we don't have any benchmarks for it other than some latency measurements. But according to this paper from Meta, the scaling laws hold even for low-bit models. Here, we're seeing 3 plots for 2-bit, 3-bit, and 4-bit quantization. The plots show the model size against its performance. Each color is a different flavor of quantization, but for simplicity, let's just look at the pink one. We can clearly see a direct correlation between size and accuracy across all 3 bit widths. So we can only assume that Microsoft's 70 billion model is much, much better than what they open sourced. And I'm sure other LLM providers will join the race. Google's Gemma 3 already comes with a version that was quantized down to 4 bits using Quantization-Aware Training, and there's no reason for them to stop there. It's also interesting to think about the incentives of the ecosystem to keep pushing the research on one-bit LLMs. Obviously, Microsoft has a vested interest in running things locally, including their GitHub Copilot and potentially Windows assistants. But now that the cat is out of the bag, there's probably going to be a lot of other providers joining the race, and I'm actually curious to see when China steps in. If you enjoyed this video, make sure to check out my other videos in this quantization mini-series, and let me know in the comments what you think about the future of one-bit LLMs. Thanks for watching, and I'll see you next time.